Okay, yeah, so some topological motivation first for like why we did this. So we work entirely I'll say we'll work entirely with smooth manifolds. And we're interested in a certain kind of question, or a certain type of question. So firstly, a pair of smooth four manifolds, let's say X and Y, is called exotic, an exotic pair. If X is homeomorphic to Y, so they're equivalent topologically, but X is not diffeomorphic to Y, so they're not equivalent smoothly. And in four-manifold topology, this discrepancy between topological equivalence and smooth equivalence is sort of like, it's at the heart of like what makes four manifolds really interesting. There are a lot of, I don't know, very important open problems, such as the smooth four-dimensional Poincare conjecture, that ask questions about this kind of discrepancy, okay? And so these discrepancies, we call these exotic phenomena. Okay. Okay, so what we want, if we want to have some shot at like finding exotic pairs, or taking two four manifolds that are homeomorphic and trying to show that they're not equivalent smoothly, we want tools that are sensitive to smooth structures. In particular, we want things, so given exotic pair, we want smooth four-manifold invariance, basically. Some tool phi such that phi of x is not equal to phi of y. Ooh, okay. Is it, or maybe I'll just use this side for now. Okay, now here is a bit of background. This is a theorem called the wall stabilization theorem. And it says the following. So let x and y be an exotic pair. And x and y are closed, simply connected four manifolds. Sure, like this. Then there exists a diffeomorphism so I'm taking the k-fold connect sum with a bunch of S2 cross S2s. So if I started with an exotic pair x and y, if I take, sufficiently many connect sums with S2 cross S2, so K is sufficiently large, then that exotic relationship is destroyed. They become diffeomorphic. Okay, they've stabilized. Okay. Okay, so if we have a tool, if we have a smooth four-manifold invariant, and it behaves nicely, I'll say behaves well with respect to the connect sum operation, then, if phi has, if it has any shot at detecting exotic smooth structures, then it must be the case that phi of S2 cross S2 is trivial somehow. And okay, so this was back in 2014 before we had figured out ways to compute Skein lasagna modules. The Khovanov Skein lasagna module over a field is an invariant. It is a tool like this that behaves nicely with respect to connect sums. And so I guess the conjecture was that the invariant vanishes for S2 cross S2. Okay. I'm sorry? It's because of the H-cobordism theorem. So if you have a homeomorphic pair, there is this object called an H-cobordism between them. And if you start with X and you go to Y through this cobordism, in the middle slice you have a manifold that looks like X connects sum a bunch of S2 cross S2s. Like connect summing S2 cross S2 is sort of the result of attaching a 5-dimensional 2 and 3 handle pair. It follows from the H-cobordism theorem. Are there any other questions? Okay. But yeah, so I guess this is just like it's motivation for computing, or why we would be interested in figuring out the Khovanov Skein lasagna module of S2 cross S2. Okay. So I know Chi-Yu talked twice already, but I want to just really quickly recall the definition of the Khovanov Skein lasagna module. Maybe recall. Okay, so given a link homology theory, let's call it Z. And by a link homology theory, what I mean is a nice functor from a category of, let's say, links in S3 and cobordisms between them in S3 times I. And so it's a functor that, given some link in S3, returns, let's say, a Q vector space. a bi-graded Q vector space. And throughout this talk, this will just be Khovanov homology the whole time. Okay. Great. So yeah, links, you get vector spaces. For cobordisms, you get linear maps. Okay, great. And so in 2019, Morrison, Walker, and Wedrich, they show that given a link homology theory like Z, we can construct a smooth four-manifold invariant called the Skein lasagna module associated to Z. And okay, does everybody remember the definition? Should I go through the definition? Is that okay? Or are we sick of the definition? I'll do it quickly. Okay, so let's just do it for Khovanov homology. So a Khovanov lasagna filling consists of the following data. So this is after you're given some four-manifold X and a link in its boundary. So this is the classic picture. So this is a picture of X, and this is the boundary of X. Let's say L is this red link in the boundary. Okay. Then a lasagna filling is the following data. So you have some finite collection of embedded disjoint four balls in the interior of X. You have a properly embedded framed surface. Let's just draw one. Maybe it has genus. And this surface intersects the S3 boundary of these four balls in some collection of links. Right, so let's call this L1, L2, L3. These are the input links. So in total we have 4s. Our collection of input links, our surface sigma. And then you attach labels from Khovanov homology, right? So at each of these input links, there is some label, let's say V1, V2, V3, where each VI is in the Khovanov homology of that input link. Okay. Right, and so the Khovanov Skein lasagna module is generated by these fillings. So let's say let's only work over Q. This is X with my link in the boundary. So it's generated by Khovanov lasagna fillings of this pair XL modulo a pretty specific relation. And this relation is the following. So So you identify fillings up to isotopy row boundary. You also impose a linearity condition in these labels. That's right, multilinearity. And then you also identify with this enclosement relation, or Skein relation, I guess. Enclosement. And this enclosement is just, imagine you had some filling like this, and in your 4 manifold, let's say there existed, for example, let's go here. Sorry, bear with me. Suppose there existed some larger 4-ball that contained all of your other input 4 balls. Okay, then on the boundary of this 4-ball, this S3 boundary, it intersects my surface sigma in some new link. I kind of drew this badly, but imagine this green is a link. Okay. Now notice that there is a piece of this blue surface that runs from this collection of input links to the big guy on the boundary. Let's call this guy in here sigma prime. Okay. We require that the label on this larger input link, this guy on the outside, let's call it V4, is equal. So remember that for cobordisms, Khovanov homology associates a linear map. There is a map from the tensor product of these labels to this guy on the boundary that's induced by this sigma prime. And so this label V4 has to be the image of these guys under that map. Does that make sense? Okay, so this is, let's say, Khovanov homology of sigma prime of V1, tensor V2, tensor V3. So that is like this extra condition on the labels. And now we can identify these 2 fillings. That is this third enclosement, roughly. Okay, so it's just like I can swallow the smaller input balls with bigger ones as long as I adhere to this rule for the labels. Okay, so that is the invariant. Great. And yeah, so a quick property. And let's say, let's have it be a theorem. I believe this is due to Manilescu and Nitholith in 2022. So I will write the Khovanov Skein lasagna module over the rationals, or over any field, of the connect sum of 2 4 manifolds. And let's say they have a link Lx and a link Ly in the boundary. This is isomorphic to the tensor product of the connect summands. Okay, so this is Skein lasagna playing nicely with connect sums, and this is why you expect it to be trivial. I guess at the time of this project, it was like not known if this invariant did detect interesting exotic smooth structures. It was like after, due to Chi-Yu, that we knew it did. So at the time, it was sort of like, okay, if this invariant is worth its salt in any way, we actually need to show that it's trivial on S2 cross S2. Because if it wasn't, there would be, you wouldn't be able to detect anything because of this theorem. Okay, does that make sense? Yeah, oh, yeah. This might be a two-hand maneuver. Nice. Okay. Yeah, and so what I want to do now is like explain. So I want to explain a couple of things. I want to explain how to compute this guy. And by explaining this, we will get to the other thing that I want to show, which is that a form of Khovanov homology for links in S1 cross S2 shows up in this computation. And at the time, it was kind of a surprise that it did. But I think looking back, it makes sense that it would. But okay, let's see what goes into computing this guy. Okay, so quick definition. So a four-dimensional two-handle body is a four-manifold obtained by, I'll say, attaching four-dimensional two handles to the four ball. And what do I mean by four-dimensional two handles? I mean you take copies of B2 times B2, and you attach these handles to B4 along the boundary of this first guy. Okay. So when I specify how I'm attaching my handle to B4, I'm attaching it along the boundary of this B2, which is an S1. I have to specify a framing. But the takeaway is we can represent two handle bodies by framed links. Also, if this is like super familiar to everybody, we can, I don't know. It's so for example, if I imagine that the blackboard is the boundary of my four ball, I can represent something like S2 times D2 as a zero-framed unknot. I can represent S2 times S2 minus a four handle as the 0-0 framed hop link. And maybe like, okay, I can do CP2 bar without a four handle as the -1 framed unknot, right? And so these are Kirby diagrams. This is like a diagrammatic language to talk about four manifolds. But for this talk, we're only interested in four manifolds that have just a single zero handle, which is this four ball, and some number of two handles attached along a link like this. Yeah, so I'm imagining the blackboard is the boundary of V4. And I'm saying, okay, I want to attach this guy. The boundary of this first bit is an S1. And so I'm saying I'm attaching this along just the unknot. That will be my attaching knot in the boundary of this four ball. And then this framing specifies roughly like how the rest of my handle is attached. Like, does it wind around or something? But this is saying it does not. And so you end up with S2 cross D2. And maybe it's like, I don't know, it's a good exercise to see why this is S2 cross S2. But does that make sense?
Let's see, why is it S2?
Why is it S2 times D2? Because, okay, so you have like a disk here, and you're attaching it along just this circle. The rest of this part does nothing, so you have your D2, but you end up with just like that S2 that you got by attaching the disk. If that makes sense.
Oh, I see.
Yeah.
The other part. Yeah.
Okay. And so as you've seen, Khovanov homology is a link invariant that you can compute combinatorially from diagrams, right? So you can start with some link, resolve all the crossings, and like you're basically just doing combinatorics and algebra to compute the thing. And maybe the moral is that Skein lasagna modules are also computable, combinatorially computable technically, from a Kirby diagram of a four manifold. And here's how. Okay, so this is another theorem of Manilescu and Neathliff from 2022. All right, so let X be a two-handle body. Let's say L, some link in the boundary. Actually, let's call this K. And suppose X is equal to my zero handle, my four ball, with some number of two handles attached, and I'm attaching along a framed link L. Okay, so there is this L, this is my Kirby diagram, and then I have some other link K in the boundary. Great, okay. Then there is an isomorphism. So, and I will say I'm being like a little bit like loose with gradings. If I don't know, maybe if there's time we can discuss gradings, but let me just write this. So the Khovanov lasagna module of this pair XL is isomorphic to the following. So you have a big sum. You have elements in k copies of the natural numbers. And you're summing over Khovanov homology groups of cables of this attaching link L. So this is Khovanov homology of cables, along with your boundary link K. And we shift by -2r. This denotes a quantum shift, this curly bracket. And we mod out by a specific equivalence relation. Does everybody know what I mean by cables here?
Sure, but these guys are on there?
No, this is like, it could be like something very crazy, right? Like this is maybe like a 2-2 cable.
Right, no, I mean L and K.
Oh, not necessarily. It might be linked with each other, depending on like how K sits in the boundary. Okay, so like, I don't know, given this isomorphism, technically you could say that like, okay, since these pieces you can compute combinatorially, you can compute this guy on the left combinatorially. But there's kind of this clear problem where you need to sort of understand Khovanov homology for all possible cables of your attaching link. And that's just like a very difficult thing to do in general.
What is the E?
Oh, sorry, this is an R? Yeah. Yes. Sorry, I should say that. Yep. So like each component itself is being cabled, right? Oh yeah. Here is this. Okay, so this equivalence relation is given by the following identifications. Okay, so there are two cobordism maps that we're interested in when it comes to cables. The first is if you have, let's say, two parallel strands that have the same orientation, then there is a cobordism like this that swaps them. So you imagine my cobordism is going from bottom to top. I'm like permuting these two parallel strands. Let's call this guy, let's just call it beta I. We'll say this is the I plus 1. An ith strand in my cable. Right, so this cobordism induces a map on the Khovanov homology of the cable of my link, and it sends it to itself. Okay, and we say that, you know, if I started with some V, some element over here, then it's identified with this permuted version, with this braid group action. Okay. Let me write that here actually.
Sorry, this is the property of Khovanov homology or something you impose it on top?
So you're imposing it here, right? Like you're taking all of the cables, and then at each Khovanov homology group, at least on this cabled guy, you're modding out by this braid group action. Okay. Okay, and there's another. So let's say phi I. We'll define this as this cobordism. So this is the cobordism that starts at nothing, and it spawns two oppositely oriented parallel strands. And for, I guess, the experts, these are technically dotted. So this, like, bundt cake map induces a map from Khovanov of the RR cable to the Khovanov homology of R plus 1, R plus 1. So maybe I should have said it. This means I have R strands oriented one way. This means I have R strands oriented the other. So this surface creates two oppositely oriented strands in my cable. And that's how I can go from one Khovanov homology of a cable to the next. And like the braid group action, we identify along this dotted bundt cake map. Okay, and that's it. So this thing, as long as X is a two-handle body, you can turn the Khovanov Skein lasagna module into a computation involving just regular Khovanov homology.
Sorry, I'm not understanding.
Yeah.
What is this two labels, LDB?
I guess I mean, yeah. So there's like R many strands in my cable going one way, and then I have R going the other.
Oh, so
It's like a big
normal
cable.
kind of
Yeah.
It's not a standard cable.
Yeah.
Okay.
Yeah, okay. Great.
And how do you show something?
Oh, it's a great proof. I mean, so the sketch is, can you go lower? Yeah, okay. Here's the sketch. Okay, so the two-handle body, so imagine this is your four-ball. This is kind of like a sort of a lie of a picture, but and imagine this guy is my two-handle that I'm attaching, right? So I have my attaching link running around here. Okay, does this schematic sort of? Okay, so then if I'm thinking about lasagna fillings, and I have this manifold, you know, I have this like crazy surface, and I have these input balls that are floating around. But what I can do is I can isotope everything into this four ball. I can just push all of the interesting topology into here. And up to isotopy, the only intersection that my surface has with this two-handle is a collection of like core parallel disks with various orientations. So I can shove everything into the four ball, and then up here I just have disks that are kind of boring. So if I have these disks, maybe this will make sense. Like I have the rest of my surface in here, and I have my four balls floating around. Here. Now the idea is, since this is just a big four ball, and we have this enclosement relation, I can just take like a giant four ball that eats everything. So I push all the interesting stuff in, and I inflate a giant four ball that eats it all. And if I push this orange all the way to the boundary, like as close as I can get, the link that I have on the boundary is a cable of the attaching link for my two-handle, okay? Because I just have these disks, right? And so from this idea, you can make an isomorphism. So what you do is you take,
Sorry,
oh yeah.
So you have your K
So is K the link on the boundary, or is it the attaching link?
Where was the K on that left-hand side?
Oh, sorry guys.
Was it now?
It's supposed to be K. That is my bad.
So you can surface it, so it's boundary K, it's the interior X, and you somehow you want to push everything away from the handle.
So the attaching link is L. Like just for the sake of this picture, suppose K is empty. Suppose there's no K.
Okay.
Then I'm saying that like if I had a generic Skein surface, if I had this weird filling for this guy, I could isotope everything, push all the interesting knotting and stuff into a giant four ball in here. Now all that's happening at this attaching region is, you know, it's a bunch of core parallel disks intersecting the boundary of this four ball in copies of my attaching link. which ends up just being cables.
Why it is just R, it can be 0R.
Oh, sure. I mean, yeah, it could be. Sorry, I just. Sure. Anyway, so then what you would do, so I have, what I could instead do is I could construct an isomorphism where I take, let's say, the Khovanov homology of a cable, and I send it to a filling in this guy, and that filling is what I get, it should be giant orange with these core parallel disks. Okay? Like
I don't understand why the cable here. Where did they come from? Why didn't they just get one copy?
It's because that's how these disks intersect my attaching region now. Right? Like I'm attaching this two-handle, I have these core parallel disks, so I'm intersecting here in my attaching link, and I'm intersecting a bunch of times. They're all like pushed off from each other. Does that make sense?
No, it doesn't. It's
Okay.
a description that. Why couldn't it have been that you just have one copy? Well, what would have gone wrong?
Yeah, I mean, there's you could have just one copy of L, but then you would also have like other skeins, right? Like I can't just have there be one disk. There could be like many disks. There are many disks. Just like generically, that's what I can do with a surface in this picture, and that plus this like enclosement relation. Okay. Any other questions? Okay, so let's try and do an example computation for S2 cross S2. Nithalith? Ikshu Nithalith? Yeah. Okay. Right, so I said before that we can represent S2 times S2 without a 4 handle as this 0, framed hop link. I will be using just a quick fact. The Khovanov lasagna module of a 4 manifold. So I'll just say it does not see 4 handle attachments. So it's enough to use this formula. Oops. Maybe I leave this.
When you say minus a 4 handle, is there another way of saying, like, what am I deleting?
Like a 4-ball.
A 4
Yeah.
ball.
Uh-huh.
Oh, a 4 ball. So I just deleted one. Okay.
Yeah. So it does not see this in particular. So I can apply this Manilescu-Nithalith like cabling formula for this diagram, and that's what we're going to try to do. Great. Okay, I need to draw kind of a crazy picture really quick. Okay, so let's do it like this. There's one small thing I need to also say. So when you make a Skein lasagna module, you're building it from a link homology theory, and that link homology theory will have some algebraic structure. It might be like bigraded or filtered or something like that. When you cook up a lasagna module, the module inherits that algebraic structure. So Khovanov homology is bigraded. The Khovanov Skein lasagna module is also bigraded. But it also has a Skein grading. So this is an extra grading. And it's graded by elements in the relative second homology of X and L. So each of these fillings has its own relative second homology class associated to it. And so this theory, you get your normal bigrading from Khovanov homology, it's inherited, but there's this extra Skein grading that comes from H2. Okay. And so if I'm specifying a Skein grading, I will write it like this. And I will be specifying a Skein grading here. So let's choose this diagram. 0, 0. Let's choose orientations so that we pick out generators of H2. And let's say alpha is 1, -2. So I guess, where did I write? Let's write this up here. So the second homology of S2 cross S2 is just 2 copies of Z. Just as an example, let's choose alpha 1, -2. And now we can compute the Khovanov lasagna module of S2 times S2. Nothing in the boundary. It's closed. And then Skein grading 1, -2 as follows. So I'm going to draw kind of a crazy picture. Let's draw it like this. Sorry, bear with me for a sec. Yep, and then this goes this way.
Can I ask again about Skein? So if you just studying Fremantle and not there, and I do surgery, then there's some kind of sum you have to, whatever data you associate to the
Sure.
boundary. Is that sum somehow related to that?
Oh.
Shadow of this, or?
Oh, I think.
Or you would say it's purely the logical.
I'm tempted to say something like, so in the 3-manifold setting, Skein lasagna is an invariant of a 4-manifold and a link in the 3-manifold boundary of that 4-manifold. There might be a sense in which the lasagna module is something that is like the Khovanov homology of L in that 3-manifold boundary. So, it does depend on which 4-manifold. Many 4-manifolds have the same boundary, but you're sort of getting a link homology theory for a link in the boundary of whatever your 4-manifold is. Does that make sense? But I don't know if that's that's more of a philosophical thing than something rigorous. Okay, sorry, I'm drawing this. Okay, so I had one going this way, 2 oppositely oriented ones. I had this guy. 1, 2, 3, 4.
So the surgery we had done is somehow inherited from the surgery on the link, right?
You mean are you saying when I attach my 4 handle, I'm really doing surgery to the boundary? Yeah, when I attach my 2 handle, I'm doing surgery to the boundary. Yeah. 3, 4, 5. This picture is so terrible. Okay. 1, 2, 3. Oh man, this one's like 3, 4. Okay, and then it just keeps going on. Okay, so I've drawn what I've called like a cabling directed system. You should think of it as like, so this arrow, if I'm going down this diagonal, I am doing this. So I guess it's my dotted annulus map on this white component. So I'm like spawning these oppositely oriented strands. And on this side, I'm doing the same, but I'm doing it on this right component. Okay, so anytime I'm going that way, I'm spawning strands on the left. If I'm going this way, I'm spawning them on the right. And I guess what I would like to do is I'm diagrammatically thinking that, man, how do I write this? Okay. Like each one of these pictures represents the Khovanov homology group of that link. Yes.
So on the very top, we have white and 2 red guy.
Mm-hmm.
Label 1 minus 2, and these like about this homologicity.
Yeah. So this Skein grading for the Manilevsky-Nicolith formula, the Skein grading determines what you start with. It determines like where your cabling begins. So I have a component of my hop link with the same orientation as this guy, and then over here I have -2. They have opposite orientations to my hop link. So this grading actually specifies my beginning diagram. Yeah. Right. And so, okay, also at each of these groups, I am modding out by this grade group action as well. So at each one of these objects, I'm saying, I can permute my strands with the same orientation. And so this picture is just a way of describing, I wish I did not erase it, the Manilevsky-Nicolith cabling formula. And so it follows that the Khovanov Skein lasagna module of S2 cross S2, nothing in the boundary, at this Skein grading, it's isomorphic to the co-limit of this big guy. Okay? Yeah, this is like, I have a Khovanov homology group of these cables, but I'm like only thinking about the parts that are fixed by this braid group action. I'm like modding out by this like swapping of strands with the same orientation. Okay. How are we doing on time? Pretty good. Okay, so if anybody is like kind of familiar with Khovanov homology, this sort of looks impossible because it's like, okay, I need to compute Khovanov homology of every conceivable cable that I can think of. Like, even though it's the hop link and that's, I guess, simple, that's still like kind of an impossible task. But we can break this problem down. Sorry. There's like one way to make this big directed system and its co-limit simpler. You consider just diagonals. So consider like, okay, what if I only took this part? Like maybe I just consider the diagonals in this big system. It is enough, so the claim is that by studying these diagonals, if I can compute what's going on just on these purple guys, I can determine what's going on for the whole thing. I'm sort of like commuting co-limits in a way. This is like a double co-limit, and I'm doing one instead of both. And so it remains, what are these diagonals? They are themselves a Skein lasagna module. So okay, so diagonals. The claim that each diagonal is a Skein lasagna module of the following form. So it's S2 cross D2 with a specific link in the boundary. Here's the Skein grading. This link, this lives in S1 cross S2, and it's this link. So here's my picture of S1 cross S2. And it's just the crossingless, geometrically essential, and component link. Whoops. Like this. Okay, any questions? So we've turned lasagna of S2 cross S2 into lasagna of S2 cross D2 with specific guys in the boundary. And we're going toward showing that's 0. So we win if we can show that these are all 0, for example, for this. That's sort of like our win condition. I guess maybe if it's not clear, like why this, each diagonal is this lasagna module, like look at what's happening. Like just say on this guy, you have the 2-component link in S1 cross S2, and all of the cabling and symmetrizing is happening on this white component. And so that cabling and symmetrizing is the thing that behaves like a 2-handle attachment. So there's one component that's special, like stuff is happening, but this other guy's just fixed, just lives in the boundary. Okay, cool. Cool. Now, in order to finish this off, I just need to say a tiny bit more background. Okay, so there exists a version of Khovanov homology for links in S1 cross S2. Okay, so normally Khovanov homology is a theory for links in S3. You need it to be for links in S3 to build a lasagna module, because that's what the boundary of your input 4 balls is. So this is by Lev Rozansky, and extended by Mike Willis.
Is it like the annular homology, so which would correspond to links in S1 like R2? And then like the Khovanov, from R3 to S3, you have to show something that would establish that it's actually variable in S1 and S2.
Yeah, I guess I'm actually not sure how this construction is related to annular Khovanov. But let me say what it is. And, yeah, I'll say what it is. So let's denote it by KHRW. And let's draw our picture. Oh man, I should have chosen. Okay. I'm going to draw my link in S1 cross S2 like this. Sorry, I'm switching notation around. So maybe this is my link. This blue line is like my surgery region. So this guy would be okay, so suppose I had some link in S1 cross S2 that looks like this. You would compute this guy. So this is just the usual Khovanov homology of the following link or object. Okay, and what this box is, this is it's called the Rosansky projector or the bottom weight projector. N is the number of strands. It's how many strands are intersecting my belt spheres here. So this is called the Rosansky projector.
So no, I don't understand. So do you think of your link as an actual grade, or there's a what is the trait for this box?
Okay, so all I mean by this picture is that whenever you have, here's your surgery region. I'm replacing all of my surgery regions by this weird complex, and then I'm taking homology of this guy. So like I could have many of these, I guess, and this could run around very crazy.
About links in S1 times S2, right?
Yes.
So L is here. L is some link that
Is the,
I mean that picture, does it correspond to basically you have some kind of a grade or maybe a tangle
yeah.
that then gets closed around as you go around S1.
Yeah, but I guess I just drew this for this picture, but like it could do crazier things for sure. Like there could be other components that are like linked with it or however you want. It's just that.
Well, you didn't tell me what L is, so but I'm still trying to. So maybe L is what? So is L some kind of tangle that has n outputs at the top and n outputs at the bottom and anything in the middle? Is that what I should be thinking?
Yes. Yes. Okay, so what is a Rosansky projector?
So the thing on the right is a link inside of R3, or is it link inside?
Right. So you've gone from an invariant of links in S1 cross S2 to an invariant of links in S3. The issue, like I'm hesitant to call this thing a link. It's a chain complex, and the reason is this thing is represented by infinitely many full twists on n strands. So it's the complex that corresponds to infinite full twists. So I mean, I guess you could think of that as a link, but it's sort of confusing to me.
It's not one group invariants by S1 times S2 up, so you can forget about the chain complex. Right. So if n is 0, I get a link in S3, right?
Yeah, it's just floating away from my surgery region.
Oh, so they're just on something that go around.
Yeah. Okay, awesome. So yeah, maybe I'll just say this is a little bit vague, but this is, so let like F TV full twists, the Khovanov complex. associated to full twists on n strands, then you can think of the Rosansky projector as a specific stable limit of these complexes. So roughly, you're just stacking full twists on each other and you're taking like a limit. And I didn't specify what the connecting maps are in this limit, but depending on your choices of connecting maps, you get different projectors. For Rosansky-Willis homology, it is this one. It's this specific choice.
So just so I'm clear, so suppose in S1 cross S2 I have these two strands linked or compound. And so that's an element on the left-hand side. So the way you taught me to manage is I cut it open and I implement full twist.
Yeah, infinitely many. Just like, yeah.
And that was a priori S2 cross R. And I just sort of take a trace from the top.
Yeah. Take the trace. Sorry, what was the link that you had in the beginning? Were you thinking?
Just the two strands.
This guy. Yeah. Yeah. So then, okay. So this is a link. I guess I erased them, but this is a link in S1 cross S2. The Rosansky-Willis homology of that guy is Khovanov homology of this. But here, I sort of do infinitely many full twists, right, in a specific way. It's just, I guess it's like, it's a non-trivial fact that this thing corresponds to some complex, but you're just inserting that complex into this picture.
So this categorifies the joint vector projector.
Yeah, that's right. So the temporally-Lieb algebra, there are like projectors of various weights when you decompose it. Right. The Jones-Wenzel projector downstairs is the highest weight projector. This is the lowest weight projector. It's the complementary projector. But yeah, it categorifies one of those. That's right. Okay. Okay, I need one kind of tricky lemma. This is due to Matt Hugenkamp. Okay, and it says the following. So the complex associated to the n-strand identity braid, so the Khovanov complex of just the identity, is homotopy equivalent to a complex that looks like this. I'll say what these are in just a sec. Let's just say Pn. Each one of these is a projector of some kind.
Sorry, what's the left?
Just the identity braid. So for the people that have seen the temporally-Lieb algebra and its projectors before, the decategorified projectors, this is a categorification let's say TL of this fact. So it's just the identity map on the temporally-Lieb algebra decomposes into its, a sum of projectors. This is the categorified version of that statement. There are many different projectors downstairs. These guys in the middle are just categorified analogs of those. And the point is, if n is even, you get Rosansky all the way at the left. And this guy over here, this is categorified Jones-Wenzel. Okay. All right. Okay, I want to leave this.
You say the one Rosonsky uses the guy on the left.
Yeah. So bottom weight projector is the S1 cross S2 invariant. Yeah, I don't know, it's kind of like the bad one, I think, because Jones-Wenzel is like very nice. I think it has nice properties, but okay. All right. Now here is a theorem. By me and Melissa Zhang. 24. The Khovanov Skein lasagna module of S2 cross D2 with some link in the boundary is isomorphic to the Rzansky-Willis homology of L tensored with the Khovanov lasagna module of S2 cross D2 with nothing in the boundary. So this was kind of the thing that was surprising. It was like we were trying to compute these. We had no idea what they were. But it turns out they recovered Rzansky-Willis. They recovered Khovanov for S1 cross S2. I should say this term at the end is negligible, but like on this first tensorial factor, that's where all the interesting stuff happens. And it will follow from this theorem.
If I take S4 and then take V4, take a link, right? Then I'll get this color homology.
Oh.
Is that the true thing?
I thought you get colored if you insert a Jones-Wenzel, right? Is it sort of the case that like colored Khovanov homology for link in S3?
No, I wasn't asking about
Oh, sorry.
I was asking about the analogous statement where on the right hand side you just get Khovanov homology. So
Oh, Khovanov homology. Oh, I see what you're saying. Yeah. Oh. It's not clear to me how to get Khovanov homology on there. Or
is there some scheme on lasagna thing that gives you Khovanov homology?
oh, the four ball. If the four manifold is the four ball.
So this is the analog of that.
Oh. No, maybe not quite, but with there's another invariant that does do something like that. It's a lasagna for S1 cross B3s instead of the four ball that recovers this. But like this is sort of a weird thing that happened.
Sorry,
That this is here. I mean, I think it's sort of weird, but
sorry,
I don't.
okay, you say it could have been S1 times B3. No. What are the so what is the statement for S1 times B3?
Oh yeah. The B4 recovering Khovanov homology is canonical, but this is like kind of a surprising weird argument.
And if I take S1 times B3, then what do I get on the right hand side?
Mystery. Very, very mysterious, yeah.
Okay.
Okay, so it'll follow from this theorem that S2 cross S2 is 0. But let me maybe I can sketch this and then like show why that implies that, and then we can wrap up. Oh, I want this still. Okay. Okay. So suppose I had a diagonal, right? Then what I have is something that looks like so say I have k strands. I have some other number of strands running through, and then I've like closed up. And I am doing something. I'm explaining why. The proof of that. like why this other weird thing with the projector pops up, and it turns out those are the diagonals here.
What is the weird thing?
Let me say, maybe it's not that weird. It was weird to me when I first saw it, but. Okay. So imagine this is one of your diagonals. So you're cabling and you're symmetrizing these red guys. But at each step, you have just like the Khovanov homology group of some cable of the hop link. Now what we can do is we can use this lemma from Hogenkamp, this like categorified idempotent decomposition of the identity. And we're just looking locally at the identity braid here. So I'm saying, like right under these belts, you replace the identity with this thing. There's maybe not a great way to draw that, so maybe I'll just draw like, I now have something that looks like this, and K. Plus 2. So on. Okay, and it's a non-trivial fact, but in the interest of time, maybe I will say the following lemma. So if there's time at the end, I can sketch this. If I is greater than 0, then the following colimit is 0. And this colimit is so I have P, N, comma, I. K many belts, and then I just keep spawning my belts here. So I'm cabling and I'm symmetrizing these red guys. But downstairs, this full twist complex, this categorified projector, stays the same. So the claim is, if I is not 0, and I do this weird cabling operation where I'm spawning new oppositely oriented strands, this whole colimit dies. Okay, so maybe I will just take that as a black box for right now. But the point is, if I continued, if I is equal to 0, this guy is the Rosansky projector. It's the bottom weight. We get the following. So let's write it like this. So this is now the projector that you use to make Rosansky-Willis homology. You've put that in this cabling colimit. So this guy doesn't vanish. What instead happens is it turns out that you can take your K belts and you can slide them down to the projector and then slide them out. This projector is a big complex of crossingless tangled diagrams, But the special thing about Pn0 is that those tangle diagrams have no through degree. There's no tangle component that goes from the top to the bottom. So everything in here looks like this kind of picture. And so I can take my belts and literally just slide them off. And so what I end up with is instead a colimit that looks like this. It's just...
Sorry, Pn0 projects on so what?
yeah. Or it projects onto stuff that has no through degree?
I mean,
Is that the right statement?
are you assuming that n is even?
I am assuming that n is even. Sorry, yes. But if n was odd, then the whole thing is 0, right? Because of this thing that I have not proven for you. The only time you have something that's non-zero is when n is even. You don't think so?
A single strand has nothing wrong.
Oh, a single strand is a single strand, like in the boundary of S2 cross D2, it's like not null homologous. So I don't like bound a surface. But this is just like an algebraic property of this kind of colimit. Yes.
Did you say that Pn0 is an infinite?
Yeah, they kind of all are their own infinite full twists. But like, yeah, an infinite full twist on one strand is like.
No, I mean for sliding out the cables.
Oh yeah. But it's sort of so imagine you had 2 strands, right? So what does 2 strands look like? So this is no full twists, and then maybe you have some. Like, what is the Khovanov complex? Okay, so this is what full twisting on 2 strands looks like. It's just these like little cup caps, and then you have some identity. Okay. Depending on how you choose your map, so maybe I choose my map so that I send identity, like I just include everywhere, or something like this. Like the choice of these maps determines how this complex looks. I could have alternatively chosen maps so that in my limit, the only things that are there are these things with through degree 0. So like, full twist, categorified Jones-Wenzel, you do have like an identity braid on one side. But Rosansky projector, you just have these. And the difference is sort of you fix a certain homological degree to like stabilize when you do this limit. Okay. Anyway, so because I can slide all my belts off, I end up with a colimit that looks like this. So remember, this is all still symmetrized. I just have a bunch of Rosansky projectors. But now I just have a bunch of belts floating around, disjoint from my projector. I've slid everything off. And now if I, close up, take homology, think of it as this colimit, this thing on the right, what I end up with is I'm taking this Rosansky projector, but I also have just like cables of my unknot that are symmetrized. So that thing that's floating around on its own, that is S2 cross D2. That's the zero-framed unknot cabling happening disjointly. Maybe that's a little strange to say, but maybe I'll draw it like this. The claim is that because I can slide things off, that implies this guy on the right is Rosansky-Willis of, I guess in this case, this link tensored with the Khovanov lasagna module of S2 cross D2. Like S2 cross D2 is over here by itself, and then over here you have Rosansky-Willis. I've like made them disjoint from each other. Okay. Are there any questions? Sorry if that was kind of terse.
Because of the sliding through,
Mm-hmm.
it looks like the linking is free, not winding around. That's fine.
Yeah, I've sort of I popped it all off. And now it's local.
But you're saying the scale of Rosansky-Willis is not invariant. So linking S3.
Yeah, it's S1 cross S2. Like if
Numerical.
yeah, if it's disjoint, then you get Khovanov homology again. Like there's nothing, there is no projector. There's no your link doesn't interact at all. It's locally a link in S3.
Right. So isn't that what's happening?
Yeah. That is what's happening here. That's what each term is. But each term here, I'm doing my bunt cake and I'm symmetrizing with the braid group action. So I'm really describing the lasagna module of the zero-framed unknot. And that's what's happening in red away from the projector. And that's how you get this. Cool. Okay, so in the last minute or so, maybe I should say, I stated this theorem for a link in general. If you put some tangle here, like the argument still goes. I can just throw a tangle on top. I can ignore it. I can just look locally, slide my belts off, and still do the same argument. Okay, let me call this lemma star. Okay, so I don't think I will get to prove this, like why this cabling thing crashes into higher order projectors and annihilates them, but I think I will end with this. So from green star, the Khovanov lasagna module of S2 cross S2 for a Skein grading alpha 1, alpha 2 is 0 when either alpha I is odd, and if both are even, then we end up with a co-limit of Rosansky-Willis homology groups okay, it maybe does not matter what I say here. I'll just say L prime. Tensored with the lasagna module of S2 cross D2 with nothing in the boundary at Skein grading alpha 2. But let's just call this object V. If I change alpha 2 to be odd, then by this result, by swapping my co-limits, my lasagna module vanishes. But if alpha 2 is odd, this guy on the right is non-zero. So it implies that this guy had to be 0. So by swapping colimits, this colimit of Rzansky-Willis homology groups is 0, and that implies that the lasagna module of S2 cross S2 is 0 for all Skein gradings. Okay, I think I will stop there. Oh my god, that was so long. Yeah, and then the next thing we did was we used this isomorphism to make a new lasagna module. Basically, it was not known whether or not this invariant was functorial. But since it is realized as the lasagna module of S2 cross D2, in a sense, it was sort of a nice trick that let us argue for functoriality of this invariant. And so once we got functoriality, you can upgrade it to its own lasagna module. Yeah. I'm sorry?
Sorry, can you explain it in a little more detail? Are you suggesting about different variants?
Yeah, so I mean,
And why would you want to think about different variants?
yeah. Oh, okay. So this is the formula for Khovanov lasagna modules with 4 balls as input manifolds for 2 handle attachments. There are formulas for 1 handle and 3 handle attachments for that setting as well. But the 1 handle formula, like both of those formulas in particular, are very difficult to work with. You need to I don't know, there's been almost no computations that have been done, and it feels impossible. The reason you would want a lasagna module built from this is that this is an invariant for links in S1 cross S2. And there's a generalized version for connect sums of
What is the proposal? We should think about what exactly?
the lasagna module built from this guy, from Rzansky-Willis homology. Okay, so it's links not in S3 but S1 cross S2. And so you can build an invariant, it's the same definition as the lasagna module, but you don't have 4 balls, you have neighborhoods of 1 complexes. You have basically S1 cross B3s instead of 4 balls. And this change from 4 ball to S1 cross B3, it changes the difficulty of these handle attaching formulas. For that invariant, if you have 1 handles and you're just a 1 handle body instead of a 2 handle body, you recover Rzansky-Willis. It's not some super complicated, impossible to compute formula. And so yeah, you have an invariant that can handle 1 handles a lot better. And that's I don't know, that is maybe the pit. What do you think, Chi? Yeah, okay. Yeah. Any other questions?